Right. So this example is, by the way, is also out of your textbook. The reason I like it and I kept it, and I really want to show you a few things here, is that it's a little bit more involved even than homework 4 that you have to complete this week. It is a part of a larger study that extends into chapter 18, but I don't want you to worry much about that. I would like to simply introduce the problem that this is a double reduction gearbox design that's already been developed. And by the way, in the industry, you may have multiple groups working on this. You may have someone designing the gears and finding the forces in the gears and providing that these numbers to a designer or shaft analyst to come up with the dimensions. So in this specific problem, we are taking the role of not designing the gears or the system, but rather designing the shafts. So it tells us already that the gears transmit the torque through keys. So we know that keys are being used, and the gears have been specified. So we're not designing the gears, allowing the tangential and radial forces transmitted through the gears to the shaft to be determined as follows. So we already know these forces. And you want to be able to read these notations carefully. It says W23T. There is a superscript T, and this means tangential. And here there is a superscript R, means radial. So they already are providing me with the tangential component and the radial component. You remember in the example I showed you earlier, we had the forces applied at an angle, and we had to find the rectangle components by resolving it into a tangential and radial components. So here the tangential and radial components are already provided. And if I'm looking specifically at the shaft that I'm concerned about, I have here the interaction between 2 and 3 and the interaction between 4 and 5 in the shaft that I'm trying to design. And this is a very important step, is coming up with a shaft layout. So you know, based on the design, that I can have a bearing put here and a bearing here, and then my gears have to be aligned with the gears at the top with gear 2 and gear 5. So you kind of know the location of the gears, the width of the gears, the center line of the gears. These are all important. So I can come up with a geometric layout as shown here. So this is a schematic of what I think my shaft is going to be. Like knowing I have to have a bearing, and this bearing is going to be resting on a shoulder. But also I want to keep it in place, and I'm going to use a snap ring. So I have a groove here. And also my gear 3, for example, is going to be resting on a shoulder. And right after it to the left, I want to have a groove. So I can also put a snap ring. And I'm copying that to the right side, where also my gear is resting on the shoulder, have a groove for a snap ring. Same with my bearing is resting on the shoulder, and then I have a groove for a snap ring. So this is basically the shaft that we want to design, and we are given the tangential and radial forces in gear 3 and gear 4. So we know the forces that are being applied, but we do not know the diameters. So the first step that we want to do here after having a schematic or a layout is to identify the material. I would just like to refresh here on some of the steps that I discussed in the lecture videos on how to design a shaft. Is to come up with a geometric layout, to choose a material that is going to work, to do the stress analysis for both static and fatigue, and to look for deflections. And I ought to say here that was something like what we're seeing on the screen. It is a bit complicated to try to do this by hand using the superposition and using the equation in the back of the book. So you're going to see us do that in the upcoming section of the course, where I'm going to introduce finite element method and ANSYS workbench. So for now, we're not going to worry about shaft deflection when we have a stepped shaft. even though you were able to do it for a prismatic shaft in homework number 2. And the last thing in shaft design was to look for vibration concerns and resonance. If you know the speed the shaft is going to rotate, you can use what you learned in the vibration class to make sure that you have no concerns in regards to vibration. So after coming up with a geometric layout, we are going to agree on a material, and as a starting point, we're using inexpensive cold-drawn steel. And as you may recall, when I introduced shaft design, I said typically steel is used for one important reason, because the steel is a rigid material. It has a high modulus of elasticity. It is not easy to twist. And remember, the main function of a shaft is to transmit power through a torque. So as it is transmitting the power, it is subjected to these high forces, and we definitely do not want it to yield. So after looking at a material, the next step would be to do our stress analysis calculations. The first step is to find the internal forces, knowing the external forces. So I do have the applied forces. I need to calculate for the support reactions. And again, I'm looking here at a problem in a static problem in 3D. So if I'm looking at equations of equilibrium in 3D, theoretically, we have 6 equations. 6 equations. Some of the forces in the X, some of the forces in the Y, some of the forces in the Z. Clearly, for this shaft, we do not have any forces acting in the X direction. So that leaves us with some of the forces in the Y, some of the forces in the Z direction. Also, we have 3 equations of moment. Some of the moment about X, which I can use here for torque equilibrium. If we know that the shaft is going at a steady speed, in this particular problem, we're not going to use this equation. So I have 2 that are left, namely some of the moment about the Y direction, some of the moment about the Z direction. So practically, I have 4 equations that we can use to find the 4 unknown support reaction components, RAZ, RAY, RBZ, and RBY, which I trust you can all do. And then we can use this sigma mx to find the torque in the shaft. And we know that they have to be the same whether you're calculating it from gear 3 or from gear 4. So I have here the torque is calculated, and again the torque extends between point G and point J. And one of the important things that I urge you all to follow and do is when you are drawing this torque diagram, shear and moment diagram, is to make sure you use grid paper and make sure you keep all the diagrams properly aligned underneath each other. Because as you're going to see shortly, I'm always going to be referencing these diagrams. I really need to know where is the torque acting. So here it is between G and J. So even in the schematic here, I'm showing that with the location of my shoulder, because yes, this point is going to be important because this is where I get the transition. This is where I'm going to need to apply stress concentration factors. So I want to see these details, and I also want to see how the internal forces are going to vary along my section. So I'm looking here at the torque diagram, showing the torque after I calculate the torque, that the torque extends between G and J. Next, I'm going to do shear and moment diagram, exactly like we did before, for both the XZ plane, XY plane, and again, we're showing everything underneath. Now, looking specifically at this problem, of course, this looks like the critical section, both from MY and MZ. And since I have a step shaft, again, it is important, if you look clearly at these dotted lines, these dotted vertical lines, these are to mark the transitions I have in my shafts. So here I have a shoulder. Here I'm going to have a groove to hold it in place. So yes, I am interested in this location, and I keep looking at numbers here. You will follow that. This is really an important step. So where I have my maximum moment, I'm not looking at a single number at the peak like we did when we had the prismatic shaft, but we are rather looking at the numbers surrounding this area where I have geometric variation because of the fact that I have a shoulder, and I also have, of course, a fillet at the shoulder, and I also have a key, and I also have a groove ring right here, because all of these may be critical locations. Does anyone have any question about that? Okay, take it, you're all good. Okay, after that, I really want to consolidate and use these two diagrams to find the resultant moment at each section. So if I start taking the square root of my squared and mz squared, that will give me the resultant. And I keep doing these at each of these sections. In doing so, I will be able to come up with this m total, or the resultant moment at each section. And again, this is very important, and I mean to put it all on one page, where I am seeing my proposed kind of the design here, proposed design. Then I am showing the critical locations, and you see these dotted line extends. I'm showing the torque diagram, and I'm showing the total moment diagram, because this is gonna dictate what my starting point and how we're gonna move from one section to another as we are designing this shaft. I repeat, when I say we're designing the shaft, we're really trying to identify the diameter of the shaft at various sections, like you're gonna do in homework 4. So I'm trying to find this D1, this D2, D3, D4, D5, D6, D7. Now here, this is a groove. Here, this is a groove. I have another groove and a fourth groove here. You see the keyway, because it said that the torque is being transmitted by a key. So this is also going to be a critical location at the end of the key. So I may want to look at this location here. Now, should I go to the left or the right? I will go to the left, because this is where I have my torque. So I want to look at the end. So I would be looking at the bending moment somewhere here, where the torque exists. So this is, I would say, this is the most important sketch I have when I'm designing a shaft, and I'm going to be making my decision based on this chart. So I should be going back and forth to this chart as needed. Now, looking at this, you kind of look at it and you are thinking, I want to start where I have my maximum moment and torque applied. So I will be definitely this is going to be an eye catcher looking here. And I think maybe the shoulder is going to be critical. So if I start with the shoulder, I'll be using this moment of 3,651 and this torque of 3,240. So we look at this and we start. What I'm going to do here is looking at these numbers. I want to come, so if I take my starting point, where the bending moment is high, and there is a stress concentration at the shoulder. Here are the numbers we picked from the diagram, the 3,651 at the shoulder, and the torsion of 3,240. I'm going to use my first iteration chart or table 7.1. So I'm looking here at a generous fillet. So I'm only using a KT of 1.7 and a KTS of 1.5. So what I'm saying here with a generous fillet is that now this is the location. If I go here, this is the location of a gear. And I'm thinking here, this gear does not have to be leaning on the shoulder. It is okay to have a bit of a fillet. It doesn't have to be completely leaning on the shoulder. So that's what I mean by using a generous fillet. And this would help me use the smaller stress concentration factor. Now, you know that KF and KFS always should be less than KT and KTS. So here we say conservatively, I'm gonna let KF be the same as KT and KFS the same as KTS. Should I apply notch sensitivity? Notch sensitivity mostly would be less than 1. I expect that these numbers should go down. But again, I want to be conservative, so I'm just using KT and KTS for KF and KFS. Next, I want to find my endurance limit, or SE, and I'm going to come up with an estimate. Now, if this is a machine shaft, I can use my equation. Here, I come up with a Ka of 0.883. Kb is the one that depends on a diameter. Since we do not know the diameter, I can again start with an estimate or use a Kb anywhere between 0.7 and 0.9. So here depict like a 0.9, which is not conservative in this case. And we're gonna see this later on. Now, since this is combined loading, Kc is equal to 1. We don't have any temperature effects, or we do not want to change the reliability. So Kd and Ke are going to be 1, and Kc is also 1. Excuse me. I calculate my SE, endurance limit, based on these factors, knowing the ultimate tensile strength for a 1020 cold drawn steel. I get a 27 kpsi. I use the equation, and you see here, this is the simplified version like the one I had on my slides. I calculate ED, and I find ED is equal to 1.65 inches. Now I'm thinking I'm conservative, and I want to use one of the standard sizes that's as shown in the appendix in the back of the book. So I either have to go above 1.65 or below 1.65. I'm thinking, being conservative, I can go below, so I go to a 1.625 inches for the diameter. Now, which diameter is that? I am at the shoulder right here, so I'm really looking at the small diameter D5. So I'm thinking here that 1.625 is going to do it for D5. Remember, this is my first iteration. So now I have to go back and revisit. So now when I revisit, I have to find the uppercase D. Now, typically, D over D should be equal to 1.2. So knowing the small lowercase d, I solve for the uppercase d, I get a 1.95. Now, if you look at the uppercase d, this is going to be my D4, which is the maximum diameter. So if this shaft is going to be machined, this is going to tell me what kind of rods I need to buy that I'm going to machine to get this step shaft out of it. So this is really an important dimension to come up with. And I'm going to round the 1.95 that I just got to a 2. So I think I'm going to use a nominal 2-inch cold drawn shaft diameter. This is what I'm going to be using. Now I can calculate an accurate D over D, and I get a 1.23. Now, a radius, the fillet radius here, R, is typically 1/10 of the smaller diameter. So I'm looking at about a 0.16 radius, which is going to give me an R over D of 0.1. So I have here R over D of 0.1, and I can use these two, D over D and R over D, and figure A15-9 to find KT. And I can use figure A15-8 to find KTS. Now, Q is something I'm going to find from figure 620. And I just want to remind you that in figure 620, you need two things. You need the ultimate strength of the material, and you also need the radius of the notch. So the radius of the notch R here is 0.16 inches. So I can use figure 620 to find Q is 0.82. And figure 621, find QS is 0.85. Now, all this is good because definitely my KF is going to be less than 1.6 and my KFS is going to be less than 1.35. When I use the equation, I find KFS to be 1.3 and KF is 1.49. So the number we use from the table were conservative, so that's good. Ka for the fatigue modulus is not changing, but Kb is. And when I use the diameter to find a Kb, please note that Kb now is 0.835, which is less than the 0.9 that we originally assumed for our first iteration. Because of that, my SE is being reduced from 27 to 25.1. Now, I really have two options, either to recalculate the diameter and see whether I'm converging or not, or simply to calculate sigma A prime, sigma M prime, and calculate a design factor, which is what we did here. So we calculated sigma A prime, sigma M prime. I use my Goodman criteria, calculate NF. I find NF is 1.56, which is fine because it's greater than 1.5, which is our targeted design factor. Now we check quickly for yielding. NY is equal to SY divided by sigma prime max. I use the conservative approach and we find the yield strands to be 2.64. Is everyone okay so far? Any questions? Okay. Good. Thank you for the thumbs up. All right. Question? Good? Okay. So next, we get to, you want to say something, Benjamin?
No, doctor, I'm good.
Right. Next, we decide, like, what is the next critical location that we want to check? So I go back to my reference chart and I'm thinking, oh, I have this key and maybe at the end of this key, this is another critical location. I have a maximum moment and I also have the torque right there. So what I want to do is move on to this other critical location. So I'm going to come here and move to check the diameter at the end of the keyway, just to the right of point I and at the groove at point K. So I'm thinking like, yes, point I to the right of it, where I have the end of the key, this is a critical location, and also I, it's, and then after that, I'll be looking at the groove. But for now, I want to look at the end of the key to the right of I. So we're going to estimate the bending moment between these 2 points. So look here, 4,316, 3,651. If you have the exact dimension of the key, we probably should be somewhere here. So I can estimate the bending moment to be 3,750. I think that's what we're going to use here. So yes, M 3,750. Now we assume the radius at the bottom of the keyway will be standard. And these are based on standard designs. So R over D is a 0.02. I do not expect you to know that, but these are standards for keyway designs. So we're learning this from this example. So should you have another keyway, I would use the same standard. So R over D is 0.02, so we can calculate radius. I find the radius of 0.035. Again, for first iteration, I'm using table 7.1, and I get a KT of 2.14. And I can calculate Q. I get a 0.65, so this brings me, KF is bringing me down to 1.74. From table 7.1, KTS is 3. I'm using my notch sensitivity to calculate KFS, it's 2.42. Now, since I already know the dimension, I can consider this an analysis problem like homework 3. So I calculate a sigma A prime and a sigma M prime. I calculate a fatigue design factor, and to our interest, I find here this to be a 1.17, which is smaller than the 1.5 that is our target. So we do have an issue right here. And here becomes the question, what should we do? We are not meeting our design criteria of having a factor of 1 1.5. Either I change the diameter of the shaft, which we were happy to use a nominal diameter of 2.0, or to change the material. If we like really the 2.0, then really I can go for a little bit of a material that has higher strength. So I say here, my conclusion is the keyway is more critical than the shoulder. And that's why for homework 4, I said it may seem like this is the most critical location, but I have to check every time I have a variation in my geometry, whether due to a keyway, a shoulder, a groove, you name it. So in this case here, instead of using a 1020, I want to keep my 2-inch diameter for the shaft, for the nominal dimension, and I'm going to try to use a 1050 cold drawn steel. That would give me an ultimate tensile stress of 100 kpsi instead of the 72 that I had earlier. Now, I don't have to worry about the shoulder because I know for sure it's going to have a design factor higher than the 1.5. But what I'll be looking at is revisiting this key, end of the keyway. So I'm going to calculate here a K A to find an SE, and my SE is going to go up to 33.3. I'm going to revisit my Q and KF. I have here a KF of 1.82. I calculate my sigma A prime, and I get 16,200. So I put here 16,200. We don't really see this having a significant effect. And I calculate NF, and I get an NF of 1.54. Now, the Goodman criteria is conservative. We will accept this as close to 1.5. So we think we are happy with this. Next, I'm going to be looking at the groove. And this is an interesting one because definitely table 7.1 gives me very high values for KF and KT. So if I look at the groove and where I have my groove, I want to show you for a second here. The groove is going to be right after the gear. And one of the important things I want to say is right after the gear here, we do not have a torque. So the torque becomes 0. So I only have completely reverse cycle from the bending moment MA. So because of that, when I'm looking at the groove, we only have an MA, right? So our equation, I'm no longer using the Goodman. I don't have a combined loading, but I can straightly use NF is equal to SE over sigma A. If I use the initial factors given in table 7.1, I calculate an NF of 1.17, which is not acceptable. So I want to revisit and use exact numbers. So I dig a little bit further into a groove specification. So we looked here at globalspec.com for appropriate groove specification for a retaining ring for a shaft diameter of 1.625. We found that the width should be 0.068 inch, the depth should be 0.048, and the corner radius at the bottom of the groove should be 0.01 inch. I use figure A1516 in the back of your book with these ratios to find a KT, and KT is a 4.3. I can also use figure 620 to find the Q. So this is going to bring my KF down to 3.15 instead of a 5. I revisit with my equation to calculate an NF, and after using the more accurate numbers, clearly my design factor now is 1.86, which is greater than 1.5. So this takes care of that critical area to the right. I move still next to check point M. So at point M, only bending is present again, and the moment is really small, but the diameter is small and the stress concentration is a high because I have a sharp fillet required for a bearing. So if I show you quickly where M is, again, I'm always referencing this chart. So now we are looking at point M right here. So this is this shoulder where the bearing sits. So I'm gonna have to use a sharp fillet radius because the bearing is leaning on this shoulder, unlike this shoulder where we had used a general fillet radius. The good news is the moment is significantly reduced. The moment is significantly reduced here. Maybe we're looking at around 1,000 and we do not have any torques. So we look here, the moment is 9,509. Everything else is a 0. Again, I use table 7.1 and I find from table 7.1 that KT is a 2.7. Now I know my R over D is going to be 0.02. I can calculate the radius. Knowing the radius and knowing the material, I can find Q. So I calculate a KF of 2.19. I look at my sigma A and I include my KF in calculating sigma A. Again, like we did in homework 3 and in the example before homework 3. Now I can calculate NF, and again, I do not need Goodman because I only have axial stresses. I find a 1.56, which is absolutely fine. Now, please note that what we did here is we used a diameter of 1 inch. 1 inch. So if I look at my shaft design, we have here 1.625 now. We have here a 2-inch diameter, and we got here a 1-inch diameter. So D6 can just have to be more than 1.2 inches. So, and it's a transition between the 1 and the 1.625. So maybe I can use like a 1.4. So I can come here and say that I can use a 1.4 for D6. Now, clearly everything to the left, if you look here, everything to the left is way less than all what's going on to the right. So whatever dimensions I used to the right are going to be more than sufficient to the left. And that's why I'm going to come here and say, well, the diameter that worked for D7, I can use it for D1. What worked for D6, I can also use it for D2. And this is exactly what we're doing here. D1 equal D7, D2 equal D6, D3 equal D5, and D4 equal a 2-inch diameter. So this is how we came up with our shaft design, taking it step by step. And this is what I expect you to do for homework 4. And I think homework 4 is going to be simpler than that. You're not going to have all these many steps. All right, with that, I would like to open it up for any questions.
So on homework 4, Doctor, I had seen that there was like a bearing, and then there was also a keyhole. So if you were going to focus our attention on one place, it would probably be the keyhole. That's the stress concentrator. But would you also want us to do that analysis on the bearing?
Okay, let me go to homework 4. So with homework 4, there is this key, right? And you're referring to the bearing, there is a shoulder. So there is a shoulder here, and there is a key here. You do not have any grooves. So I would like you to check. You have already the moments. Sorry, I didn't share my screen. Okay, so I was referring here to this keyway, right? And the shoulder. And all these are going to be critical locations. Is that your question, Benjamin?
Yes.
Okay, so yes, you will need to check at the end of the keyway, and you're gonna need to check at the shoulder if your maximum moment, and also at looking at the bearing, you're gonna have a high bending moment and a shoulder. So you'll be calculating this lowercase d, this uppercase d, and you probably want to verify every time there is a change in the geometry. But I know that this is going to be kind of the most critical area, so that's why I think it's not going to be as lengthy as the example we just did.